Chapter 1. Early Life. Isaac Newton was born on January 4, 1643, in the small village of Woolsthorpe, Lincolnshire, England. He was born prematurely and was so small that no one expected him to survive. His father, also named Isaac Newton, had died a few months before his birth, leaving his mother, Hannah Esco, to raise him alone. Isaac grew up in a farming family. The family's farmhouse, now called Woolsthorpe Manor, was surrounded by beautiful countryside. As a child, Isaac spent a lot of time exploring nature and the world around him. He would often wander through the fields, observing plants and animals, and marvelling at the wonders of the sky. Isaac was not particularly interested in farming. Instead, he was drawn to other activities. He loved reading books, especially those about science and mathematics. He also had a creative side, showing an early talent for drawing and making models. Young Isaac enjoyed crafting sundials, windmills, and other small machines. In his early years, Isaac was not very sociable and preferred spending time alone, thinking and experimenting. His mother would often worry about him because he was so different from other children his age. Despite these concerns, it was clear that Isaac had a curious mind and was always eager to learn more about the world. When Isaac was 3 years old, his mother remarried and moved to a nearby village, leaving him in the care of his grandparents. He missed his mother greatly and felt a deep sense of loneliness. These experiences helped shape Isaac's character, making him more independent and self-reliant. In the next part of this chapter, we will explore Isaac Newton's school days in Grantham and how his early education further shaped his intellectual development. At the age of 12, Isaac Newton was enrolled at the King's School in Grantham, a nearby market town. This marked a pivotal moment in Isaac's life, as it was here that his intellectual talents started to blossom. The King's School was one of the best in the area, and it provided Isaac with an education that was a world away from the farming life he knew at Woolsthorpe. As a student, Isaac was not initially the top of his class. He was more interested in his personal projects and experiments than in the traditional school curriculum. However, an incident with a school bully led to Isaac focusing more on his studies. After being kicked by the school bully, Isaac challenged him to a fight and won. From that point onwards, Isaac decided to compete not with fists, but with brains. He committed himself to his studies, quickly rising to the top of his class. Isaac's curiosity led him to read extensively beyond the school syllabus. He was particularly fascinated by books on natural philosophy, which we now call science. He began to explore more complex ideas in physics, astronomy, and mathematics. This was unusual for someone of his age at that time, but Isaac was not a typical student. It was also during his time in Grantham that Isaac began to conduct his own experiments. He would often be found at home working on various inventions. He made a model of a windmill, inspired by a real one being built nearby. He even created a working clock that was powered by water. His room was filled with tools and materials for his inventions, hinting at the great scientist he would become. Isaac also developed a deep fascination with the sky and celestial bodies. He spent countless hours studying the stars, using a small telescope he had bought. He even predicted the timing of a solar eclipse, impressing his fellow students and teachers. Isaac's time at Grantham was instrumental in shaping his scientific and mathematical interests. However, his mother planned to pull him out of school to become a farmer. Fortunately, his schoolmaster recognized his potential and persuaded his mother to let him continue his studies. This decision would prove critical to his future achievements, setting him on a path to Cambridge University, where he would make some of his greatest discoveries. In the next section, we will delve into Newton's studies at this esteemed institution. At the age of 19, Isaac Newton entered Trinity College, Cambridge University, in 1661. This was a significant step in his life, marking the beginning of a long association with one of the world's most prestigious academic institutions. When he arrived at Cambridge, Isaac was not initially a standout student. He was what was known as a subsizar, which meant that he received a scholarship in exchange for performing certain duties, such as cleaning for wealthier students. Despite this humble start, Isaac was not discouraged. He threw himself into his studies with a passion that was both intense and focused. Cambridge was a place of intellectual ferment in the 17th century, and it had a profound influence on Isaac. It was here that he encountered the works of the greatest thinkers of his day, such as René Descartes and Francis Bacon. Their writings, especially on mathematics and natural philosophy, deeply influenced his thinking and inspired him to explore these subjects further. However, Isaac was not just a passive recipient of knowledge. He was an active learner, always questioning and probing. This led him to go beyond what was taught in his classes. He often spent long hours in the library, reading books on subjects that intrigued him. He also conducted experiments to test the theories he was learning. Perhaps the most important event during Isaac's time at Cambridge was when he came across the works of the mathematician Euclid. The simplicity and precision of Euclid's geometrical proofs captivated him. This encounter sparked a lifelong passion for mathematics, which would later become a key tool in his scientific investigations. It was also at Cambridge that Isaac began developing his theories on calculus. He realized that traditional mathematics was not sufficient to solve some of the problems he was interested in, especially those related to motion and change. This led him to invent a new branch of mathematics, which he initially called the method of fluxions. In 1665, when the Great Plague hit England, Cambridge University closed down, and Isaac returned to Woolsthorpe. This period, often referred to as the Annus Mirabilis, or the Year of Wonders, was a productive time for Isaac. He continued to work on his mathematical theories and started formulating his revolutionary ideas on gravity. Isaac Newton's time at Cambridge was transformative. It was here that his genius truly began to emerge, setting the stage for his future groundbreaking discoveries. The university would later recognize his contributions by appointing him as the Lucasian Professor of Mathematics, a position he would hold for over 30 years. But before that, there was much more to come in the extraordinary life of Isaac Newton. Chapter 2. Discovering Calculus. Isaac Newton's fascination with mathematics was sparked during his time at the King's School in Grantham and further nurtured at Cambridge University. Through his studies, Newton understood that mathematics was the key to explaining the natural phenomena he observed around him. It was a language that described the universe in a way that words could not. In the early days of his mathematical exploration, Newton was deeply influenced by the works of ancient Greek mathematician Euclid. Euclid's Elements, a 13-book series, was the foundation of Newton's mathematical knowledge. Euclid's geometric proofs, based on a logical progression of theorems, were simple yet elegant. Newton was captivated by the precision and logical beauty of Euclidean geometry. However, as his understanding deepened, Newton started to find limitations in the existing mathematical methods. His interest in physics and astronomy led him to problems that required understanding changes in motion, something traditional mathematics struggled to explain. For instance, the speed of a falling apple or the orbit of a planet around the sun required an understanding of quantities that were continually changing. This is where Newton's genius shone through. Not one to be hindered by the limitations of existing knowledge, Newton began to explore new mathematical ideas. He started to develop mathematical methods that could handle these changing quantities. During this time, Newton wrote a series of papers on mathematics and natural philosophy, which were the early signs of his groundbreaking work on calculus. As Newton dove deeper into the world of mathematics, he grew frustrated with the gap between the theoretical and the practical, the static and the dynamic. He needed a tool that could help him understand not just the state of things, but also how they changed and moved. This need drove Newton's mathematical explorations and led to his creation of a whole new field of mathematics. In the next section, we'll delve into how Newton developed his method of fluxions, an early form of what we now know as calculus. This revolutionary mathematical tool would become crucial to Newton's later scientific discoveries and change the course of mathematics forever. Newton's journey towards developing calculus, which he initially called the method of fluxions, began during his hiatus from Cambridge University due to the Great Plague in 1665 to 1666. These were formative years for Newton, often referred to as his Annus Mirabilis, or Year of Wonders. The method of fluxions was Newton's approach to understanding and calculating change. The word fluxion was derived from the Latin word fluxus, which means flow. Newton used this term to describe the continuously changing quantities he was studying. In essence, Newton was trying to find a mathematical way to represent motion and change. Imagine a point moving along a curve. At any moment, the point has a particular position, but that position is constantly changing. Newton wanted to understand not just where the point was, but also how fast it was moving. He conceptualized an infinitesimal change in the position of this point, which he called a fluxion. Newton then considered the ratios of these tiny changes, which he referred to as moments. By studying these moments, Newton could mathematically model how things change and move. It was not an easy task, though. There were many challenges and complexities to consider. The idea of dealing with infinitesimally small quantities was quite radical at the time, and it required a significant leap of imagination and logic. Newton's method of fluxions was his version of what we now know as differential calculus. It allowed him to calculate rates of change, which is crucial in many areas of physics, such as understanding the motion of planets or the fall of an apple from a tree. His work laid the foundation for integral calculus as well, which deals with areas, volumes, and other total quantities. It's worth noting that while Newton was developing his method of fluxions, on the continent, the German philosopher and mathematician Gottfried Wilhelm Leibniz was independently working on a similar mathematical tool. This would eventually lead to a fierce controversy over who was the true inventor of calculus, which we'll discuss in the next part. Regardless of the controversy, there's no denying the significance of Newton's work. The invention of calculus marked a turning point in the history of mathematics and science, providing a tool that could describe the world in unprecedented detail. Newton's method of fluxions, or calculus as we now call it, would become an indispensable tool in the arsenal of scientists and engineers for centuries to come. While Newton was pioneering his method of fluxions in England, across the English Channel, German mathematician Gottfried Wilhelm Leibniz was independently developing a similar mathematical tool. This simultaneous discovery would eventually lead to one of the most famous controversies in the history of mathematics, the dispute over who invented calculus. Leibniz began working on his version of calculus around 1674, a few years after Newton developed his method of fluxions. However, unlike Newton, Leibniz published his work on calculus in 1684 and 1686, making it widely available to the scientific community. Leibniz's notation was also more straightforward and easier to use than Newton's, which made it more popular among scientists and mathematicians. The controversy began in 1699 when a Swiss mathematician, Fétiot de Dullier, accused Leibniz of plagiarizing Newton's work. Leibniz, naturally, denied these claims, setting off a bitter dispute that would last for many years. The heart of the dispute was the principle of priority, who had invented calculus first. Newton had undoubtedly developed his method of fluxions before Leibniz started his work on calculus. However, Newton did not publish his work until much later, in 1704. On the other hand, Leibniz had published his work earlier and had thus introduced the mathematical community to calculus. The controversy became quite heated, with each side gathering supporters and engaging in bitter exchanges. The Royal Society, of which Newton was a member and would later become president, conducted an investigation and unsurprisingly sided with Newton. However, many on the European continent supported Leibniz. The dispute took a toll on both Newton and Leibniz and did not end even with their deaths. It continued to divide the mathematical community for many years. Today, historians generally agree that both Newton and Leibniz independently invented calculus. They each brought different perspectives and notations to the field, both of which are still in use today. In fact, the notation we use in calculus today is primarily that of Leibniz, while many of the underlying concepts are based on Newton's work. While the controversy might have tarnished their relationship, there's no denying the immense contributions both Newton and Leibniz made to mathematics and science. Their work on calculus was a significant leap forward, providing a powerful tool to understand and describe the world around us. Chapter 3. The Law of Gravity. One of the most famous stories associated with Isaac Newton is the tale of the falling apple. While the story has taken on a somewhat mythical status over the centuries, it serves as a powerful illustration of Newton's curiosity and his ability to draw profound insights from everyday events. The incident took place in 1666, when Newton was at his family home in Woolsthorpe, during the period of isolation due to the Great Plague. According to the story, Newton was sitting under an apple tree in his garden when he saw an apple fall straight down to the ground. While anyone else might have dismissed this as an ordinary event, for Newton, it sparked a chain of thoughts that would eventually lead to the formulation of the law of gravity. The falling apple made Newton wonder why it fell straight down, rather than off to the side or upwards. Why did the apple always fall to the ground? This simple observation led him to ponder on the invisible forces that must be at work, guiding the apple's fall. Newton started to think about the forces of nature in a new light. He began to consider that the same force that pulled the apple to the ground might also be responsible for keeping the moon in orbit around the Earth. This was a revolutionary idea. At the time, people believed that different sets of laws governed the heavens and the earth. Newton, however, proposed that the same laws applied to both. This realization led Newton to formulate his law of universal gravitation. He proposed that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This was a groundbreaking concept that fundamentally changed our understanding of the universe. It's worth noting that the story of the apple did not emerge until later in Newton's life. The first account came from Newton's friend and biographer, William Stukeley, who wrote that Newton told him the story in 1726. While the story might have been somewhat embellished over the years, the falling apple remains a powerful symbol of Newton's scientific genius and his ability to derive profound truths from the world around him. In the next part, we will delve into how Newton formulated and proved his law of universal gravitation, forever changing the way we understand the universe. After the falling apple incident, Isaac Newton spent several years contemplating the nature of this invisible force that caused the apple to fall to the ground and kept the moon in orbit. This deep thought process led to the formulation of his law of universal gravitation. Newton hypothesized that the force that caused the apple to fall to the ground was the same force that kept the planets in their orbits around the sun. This was a radical idea at the time, contradicting the common belief that different laws governed the earth and the heavens. Newton's law of universal gravitation states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. In simpler terms, this means that the larger the mass of the objects and the closer they are to each other, the greater the gravitational pull between them. But how did Newton prove this theory? He turned to the moon. Newton knew the moon was approximately 60 times farther from the Earth's center than objects on the surface of the Earth. He reasoned that if his law of gravitation was correct, the force of gravity on the moon would be 1/602nd, or about 1/3600 times the force of gravity at the Earth's surface. To prove this, Newton had to compare the moon's acceleration due to gravity with the acceleration of objects at the Earth's surface. This was where Newton's mathematical prowess and his development of calculus played a crucial role. Newton knew that the moon orbited the Earth in a nearly circular path, so he could calculate its centripetal acceleration, the inward force needed to keep an object moving in a circular path. After extensive calculations, Newton found that the moon's acceleration matched the expected value based on his law of gravitation. This was a monumental moment, providing the first strong evidence that his law was correct. Newton's law of universal gravitation was truly revolutionary. It provided a unified explanation for earthly physics and celestial motion, something that had eluded scientists for centuries. It showed that the same laws of physics applied everywhere in the universe, laying the groundwork for much of modern physics. In the next section, we will explore the impact of Newton's law of gravity and its enduring significance in the scientific world. The formulation of the universal law of gravitation was one of Isaac Newton's most significant contributions to science. It was a revolutionary idea that fundamentally reshaped our understanding of the universe and laid the foundation for much of modern physics. Prior to Newton, the prevailing belief was that different sets of laws governed the earth and the heavens. Newton's law of gravity unified these realms, showing that the same physical laws applied both on earth and in the cosmos. This was a groundbreaking concept that marked a significant shift in scientific thought. Newton's law of gravitation did more than just explain why apples fall to the ground or why the moon orbits the earth. It provided a framework that could be used to understand the motion of all objects in the universe. With this new tool, scientists could calculate the orbits of planets, the trajectories of comets, the tides of the sea, and much more. It paved the way for future scientists, like Albert Einstein, to further our understanding of gravity and the fabric of space and time. Beyond the realm of physics, Newton's law of gravity also had a profound impact on other fields of study. In astronomy, it helped explain the movements of celestial bodies and led to the discovery of new planets. In engineering, it is crucial for designing vehicles and structures, from cars to skyscrapers to spacecraft. Even in biology and medicine, understanding gravity is essential for studying bodily functions and developing treatments. Furthermore, Newton's approach to scientific inquiry left a lasting legacy. His rigorous application of experimentation, mathematical analysis, and logical reasoning set a standard for scientific method. His work embodied the principles of the Enlightenment, a period characterized by an emphasis on reason and individualism rather than tradition. The impact of Newton's law of gravity continues to be felt today. Despite being formulated over 3 centuries ago, it remains a vital tool in modern physics and astronomy. It continues to guide space exploration, helping scientists chart the course of spacecraft and explore the mysteries of the universe. In the following chapters, we will delve into some of Newton's other major contributions to science, including his work on optics and his formulation of the 3 laws of motion. These achievements, along with his law of gravity, cement Newton's place as one of the most influential figures in the history of science. Chapter 4. The Principia. The Philosophia Naturalis Principia Mathematica, often referred to simply as the Principia, is undoubtedly one of the most important works in the history of science. Its publication marked a watershed moment in human understanding of the physical world. This part will delve into Isaac Newton's journey to write this monumental work. The inception of the Principia can be traced back to a question posed by the English astronomer Edmund Halley in 1684. Halley was discussing celestial mechanics with his colleagues at the Royal Society when he wondered what kind of curve would be described by a planet if the force of attraction towards the Sun decreased as the square of the distance. Unable to answer this question, Halley decided to ask Newton, who was already known for his mathematical acumen and his work on calculus. Halley travelled to Cambridge to meet Newton and asked him the question. To his surprise, Newton immediately replied that the curve would be an ellipse, a conclusion he had already derived but had not yet published. Halley asked him how he knew this, and Newton replied that he had calculated it. However, when he tried to find the calculations among his papers, he couldn't locate them. Impressed by Newton's insight, Halley urged him to organize his notes and publish his findings. Newton initially hesitated, given his aversion to controversy and public criticism. However, Halley was persistent and offered to personally finance the publication. Encouraged by Halley's support, and seeing an opportunity to present his work to a broader audience, Newton finally agreed. The task of writing the Principia was enormous. Newton set out to present a comprehensive framework of the universe, grounded in mathematical laws. This entailed refining his theories, performing calculations, and presenting the material in a clear and logical manner. The writing process was intense and absorbed Newton completely. He was known to have been so engrossed in his work that he often forgot to eat or sleep. Despite the intensity of the task, Newton's dedication was unwavering. The first edition of the Principia was completed in less than 18 months, a testament to Newton's singular focus and intellectual prowess. The Principia was published in 1687, and it laid the groundwork for classical physics. Its 3 books contain Newton's laws of motion, his law of universal gravitation, and a detailed analysis of the motion of heavenly bodies. In the next part, we will delve into the content and structure of the Principia, exploring the revolutionary ideas that Newton presented in this seminal work. The Philosophia Naturalis Principia Mathematica is a work of unparalleled significance in the history of science. Across its 3 volumes, Isaac Newton laid out the fundamental principles of physics that continue to guide our understanding of the universe. The Principia is divided into 3 books, each addressing different aspects of physics and celestial mechanics. Laws of motion. The first 2 books are largely devoted to explaining and proving the laws of motion. Newton put forth 3 laws, which together form the bedrock of classical mechanics. First law, law of inertia. An object will remain at rest or move in a straight line at a constant speed unless acted upon by an external force. This law introduced the concept of inertia, the resistance of an object to any change in its state of motion. Second law, law of acceleration. The force acting on an object is equal to the mass of the object multiplied by its acceleration. This law established the proportional relationship between force, mass, and acceleration. Third law, law of action and reaction. For every action, there is an equal and opposite reaction. This law highlighted the inherent symmetry in forces, a principle that is fundamental to understanding interactions between objects. Book 3. The System of the World. In the third book, Newton applies the laws of motion to the real world, explaining various phenomena observed in the universe. The crowning jewel of this section is the law of universal gravitation, which states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The Principia was revolutionary not just for its content, but also for its approach. Newton insisted on grounding his theories in empirical evidence and mathematical rigor, an approach that helped to establish physics as a distinct scientific discipline. He also used calculus, or his method of fluxions, a mathematical tool he had developed to prove his theories, though he presented the final work using classical geometric methods to make it more accessible to his contemporaries. In the final part of this chapter, we will delve into the impact of the Principia on the world of science and how it established Newton's reputation as one of the greatest scientists of all time. The publication of the Philosophia Naturalis Principia Mathematica in 1687 was a momentous event in the history of science. Its reception and impact, both immediate and long-term, were profound and far-reaching. Immediate reaction. The immediate reaction to the Principia was largely positive among those who could understand it. The complexity of the mathematics and the innovative nature of the ideas presented made it challenging for many to fully grasp. However, those who could appreciate the work recognized its significance. Edmund Halley, who had encouraged Newton to write the Principia and had financed its publication, was among its most enthusiastic supporters. Despite the initial positive reception, the Principia also sparked controversy. The most notable was the dispute with German mathematician Gottfried Wilhelm Leibniz over the invention of calculus. Both Newton and Leibniz had developed versions of calculus independently, leading to a bitter feud over who should receive credit. Long-term impact. The long-term impact of the Principia cannot be overstated. The work revolutionized science and established Newton as one of the greatest scientists of all time. The Principia provided a unified framework for understanding the physical world. It brought together the laws of motion and the law of universal gravitation into a coherent system that could explain a wide range of phenomena, from the fall of an apple to the motion of planets. This was an enormous leap forward in the scientific understanding of the universe. Moreover, the Principia helped set the standards for scientific method. Newton's insistence on empirical evidence and mathematical proof set a precedent for future scientific inquiry. His work embodied the spirit of the Enlightenment, an era characterized by reason and the pursuit of knowledge. The principles laid out in the Principia formed the foundation of classical physics and remained largely unchallenged until the 20th century, when Albert Einstein's theory of relativity brought about a new understanding of gravity and motion. Nevertheless, Newton's laws continue to be used in most areas of physics and engineering, and they are accurate enough for most practical purposes, such as designing buildings, predicting planetary motion, and launching satellites. In the centuries since its publication, the Principia has continued to inspire and guide scientific inquiry. Its impact is reflected in every corner of the physical sciences, and its principles continue to shape our understanding of the universe. It stands as a testament to Newton's genius and remains one of the most important works in the history of science. Chapter 5. Later Life and Achievements. Isaac Newton's association with the Royal Society, an organization dedicated to the advancement of scientific knowledge, was a significant part of his later life and career. He made substantial contributions to the society, cementing his legacy as a leading figure in the scientific community. In 1671, Newton was elected a Fellow of the Royal Society, an honour given to individuals who have made a substantial contribution to the improvement of natural knowledge, including mathematics, engineering science, and medical science. This was a significant milestone in his career, recognizing his growing reputation as a leading mathematician and physicist. Initially, Newton was known in the society primarily for his work in optics. His early presentations involved a new kind of reflecting telescope he had invented, which used mirrors rather than lenses to gather light. This type of telescope, now known as a Newtonian telescope, provided clearer images than the refracting telescopes used at the time. Newton's design revolutionized astronomy and is still used in many telescopes today. Newton's involvement with the Royal Society deepened over time. In 1686, he presented the first book of the Principia to the Society. This marked the beginning of his worldwide recognition as a leading scientific figure. In 1703, Newton was elected President of the Royal Society, a role he would hold for the next 24 years until his death in 1727. His presidency was marked by a number of significant changes. He took steps to professionalize the society, implementing stricter admission standards and demanding rigorous scientific evidence for any claims made. He also strengthened the society's international connections, corresponding with other scientific societies and leading scientists across Europe. One of Newton's most significant contributions during his presidency was overseeing the publication of the second edition of the Principia in 1713. This edition, which included corrections and revisions, further solidified the Principia's place as a cornerstone of scientific thought. Despite his many contributions, Newton's time at the Royal Society was also marked by controversy. His disputes with other scientists, most notably with Gottfried Leibniz over the invention of calculus, were often played out within the society. These conflicts, while detrimental to Newton's relationships with some contemporaries, did not diminish his overall influence and contributions to the Royal Society and the broader scientific community. In the next part of this chapter, we will explore Newton's role as Warden and then Master of the Royal Mint, positions that allowed him to apply his scientific and mathematical knowledge in a practical context. In 1696, Isaac Newton was appointed Warden of the Royal Mint, a position he held for 3 years before becoming the Master of the Mint in 1699, a role he served in until his death in 1727. Although these roles may seem far removed from his scientific pursuits, Newton applied his remarkable intellect to these positions, leading to significant reforms in England's monetary system. Warden of the Mint. As Warden, Newton's primary responsibility was to combat counterfeiting, a significant problem in late 17th century England. Counterfeit coins not only caused economic instability, but they also undermined confidence in the English monetary system. Newton took this role very seriously. He became a tireless and meticulous investigator, going undercover at times, to track down and prosecute counterfeiters. His rigorous efforts led to several successful prosecutions, demonstrating his commitment to restoring trust in the country's currency. Master of the Mint. Newton's promotion to Master of the Mint in 1699 was a testament to his successful tenure as warden. The position of Master was more administrative and carried greater responsibilities, including overseeing the production of coins. One of Newton's most significant contributions during his time as Master was overseeing the Great Recoinage of 1696 to 1699. This massive operation aimed to replace all circulating coins with new ones made of higher quality silver. Newton's mathematical and organizational skills were crucial in this effort. He introduced rigorous testing methods to ensure the purity and weight of the silver used in the new coins, bringing a scientific approach to the process. Furthermore, Newton recognized the importance of standardizing the minting process to ensure consistent quality. He championed the use of the milled-edge coin, which was harder to counterfeit and had a more standardized weight than the hammered coins previously in use. Newton also played a key role in establishing the gold standard in 1717. Recognizing the need for a more stable and predictable monetary system, he suggested setting a fixed price for gold in terms of the country's currency, effectively putting England on a gold standard. This was a groundbreaking decision that had a lasting impact on the country's economic stability and growth. Despite these considerable achievements, Newton's tenure at the Mint is often overshadowed by his scientific accomplishments. However, his work at the Mint illustrates his remarkable versatility and the breadth of his genius. From science to public service, Newton left an indelible mark on the world. In the next part of this chapter, we will look at Newton's final years and his enduring legacy. Isaac Newton's contributions to science, mathematics, and public service culminated in his receiving a knighthood in 1705. This made him Sir Isaac Newton, an honorific he carried with pride for the rest of his life. The knighthood was a recognition not only of Newton's groundbreaking work in physics and mathematics, but also of his service as Master of the Royal Mint and his leadership as President of the Royal Society. It symbolized the high esteem in which he was held by his peers and the monarchy. Final years. Newton's later years were marked by a continuation of his work in various capacities. As Master of the Mint, he continued to oversee England's coins until his death. As President of the Royal Society, he influenced the direction of scientific research and discourse. His intellectual curiosity did not wane with age, and he remained an active participant in scientific and philosophical debates. Despite his achievements and recognition, Newton's final years were also marked by solitude. He never married or had children and lived a relatively secluded life. He was deeply affected by the death of his niece, Catherine Burton Conduit, who had lived with him for many years and managed his household. Passing and legacy. Newton passed away in his sleep on March 20, 1727. He was buried in Westminster Abbey, an honour reserved for notable figures in British history. His monument there depicts him holding a copy of the Principia, a fitting tribute to the man who had done so much to advance our understanding of the universe. Isaac Newton's legacy is as vast as it is profound. His laws of motion and universal gravitation form the foundation of classical physics. His work in optics and mathematics has had far-reaching implications across a range of scientific disciplines. His leadership at the Royal Society helped shape the course of scientific inquiry, and his work at the Royal Mint brought about significant improvements to the English monetary system. Newton's ideas have transcended time, continuing to inspire scientists and researchers centuries after his death. His life and work embody the spirit of scientific inquiry and the relentless pursuit of knowledge. His story is a testament to the power of human curiosity and intellect, and his contributions to science and society remain unmatched. Chapter 6. Newton's Legacy. Isaac Newton's influence on science is immeasurable. His groundbreaking work in the fields of physics, mathematics, and astronomy has shaped our understanding of the natural world and laid the foundations for centuries of scientific progress. Physics. In physics, Newton's laws of motion and universal gravitation established the framework for classical mechanics, which describes the motion of bodies under the action of a system of forces. His laws provide a mathematical description of the way physical objects move and interact, and they are fundamental to our ability to predict the behavior of physical systems, from the trajectories of thrown balls to the orbits of planets. Even with the advent of quantum mechanics and Einstein's theory of relativity in the 20th century, which offer more accurate descriptions of the physical world at very small and very large scales respectively, Newton's laws remain crucial for most practical engineering calculations and are still used extensively in many areas of science. Mathematics. Newton's development of calculus provided a powerful new mathematical tool for describing change and motion. This branch of mathematics is essential in physics, engineering, economics, computer science, and many other fields. Although Newton's notation for calculus isn't commonly used today, the fundamental concepts he developed, such as differentiation and integration, are cornerstones of modern calculus. Astronomy. In astronomy, Newton's work on the laws of motion and gravity allowed for precise predictions of celestial movements. His law of universal gravitation was the first to provide a unified description of the motion of both terrestrial objects and celestial bodies. Furthermore, his reflecting telescope design significantly improved the quality of astronomical observations. Legacy in science. Newton's method of inquiry, insisting on the primacy of observational data and the use of mathematical reasoning in developing theories, helped to define the scientific method, which is still in use today. His work has not only provided us with the tools to explore the universe, but also set the standards for scientific inquiry. Newton's influence on science is evident in every physics classroom, every space mission, and every piece of modern technology. His laws of motion and gravity form the basis of our physical understanding of the universe, and his mathematical innovations continue to enable new scientific discoveries. In the next sections, we will delve into how Newton's work influenced areas outside of science and how his ideas continue to shape our world. Today, Isaac Newton is widely recognized as one of the most influential scientists who ever lived. His contributions to physics, mathematics, and astronomy have shaped centuries of scientific progress. Even as modern science has advanced and new theories have emerged, Newton's work remains a vital foundation. Let's explore how modern scientists view Newton's contributions. In physics. In the realm of physics, Newton's laws of motion and universal gravitation are as fundamental today as they were when first presented. Despite the development of Einstein's theory of relativity, which provides a more comprehensive explanation for gravitational interactions, particularly at very high speeds, or in the presence of massive objects, Newton's laws still apply in most everyday circumstances. They are extensively used in engineering, space travel, and any field where precise calculations of motion are required. In mathematics, calculus, co-developed by Newton, remains an indispensable tool in modern mathematics and is extensively used across all scientific disciplines. Engineers use it to model systems and predict how they will behave. Economists use it to find optimum investment strategies. Biologists use it to model population dynamics. While the notation has evolved and the theory has been rigorously formalized since Newton's time, the fundamental concepts remain the same. In astronomy, Newton's laws of motion and gravity are still at the heart of celestial mechanics, the study of the movements of celestial bodies. They have been used to predict the appearance of comets, the motion of planets, and the existence of Neptune based on perturbations in Uranus's orbit. Even with the advent of general relativity, Newton's laws are sufficiently accurate for most astronomical calculations. The scientific method. Beyond his specific contributions to physics, mathematics, and astronomy, Newton's approach to science has had a lasting impact. He insisted on observational evidence, used mathematical reasoning to develop theories, and valued rigorous testing of those theories. This method, which helped to shape the scientific process, is still at the heart of how science is conducted today. Modern critiques. Modern perspectives on Newton's work also include some critiques. Some scientists argue that Newton's notion of absolute space and time, which underpin his laws of motion and gravity, is no longer tenable given Einstein's theories of relativity. Others point out that while Newton's laws work well for macroscopic objects, they don't accurately describe the behavior of particles at the quantum level. Despite these critiques, there's no denying the revolutionary nature of Newton's work, or its ongoing influence. His theories have shaped our understanding of the natural world, and continue to enable scientific progress. His legacy lives on in every corner of modern science, from the classroom to the cutting edge of research. In the next section, we will discuss Newton's influence beyond the sciences. While Isaac Newton is best known for his revolutionary contributions to science, his influence extends beyond the realms of physics and mathematics. He also made significant contributions to other fields, including philosophy, theology, and public administration. Let's delve into these lesser-known aspects of Newton's legacy. Philosophy. In philosophy, Newton's work laid the groundwork for the Enlightenment, a period marked by a shift towards reason and away from tradition. His scientific method, based on observation, experimentation, and mathematical reasoning, greatly influenced the philosophical movement known as empiricism, which argues that knowledge comes primarily from sensory experience. The influence of Newton's ideas can be seen in the works of many Enlightenment philosophers. For example, Voltaire, a prominent French philosopher, was a strong proponent of Newton's scientific achievements and played a crucial role in popularizing his ideas in Europe. Furthermore, Immanuel Kant's metaphysical works were significantly influenced by Newtonian physics. Theology. Newton was a deeply religious man and devoted significant time and energy to the study of theology and alchemy. His religious views were somewhat unorthodox for his time. He rejected the doctrine of the Holy Trinity and leaned towards Arianism, which emphasizes the oneness of God. This aspect of his life was largely kept secret, as his beliefs could have led to serious repercussions in his time. Newton's theological writings, which were published posthumously, offer insights into his interpretation of the Bible and his beliefs about the nature of God and the universe. He believed that religious knowledge and philosophical understanding were intimately linked, and that his scientific pursuits were a way of uncovering the divine order of the universe. Public administration. As Master of the Royal Mint, Newton demonstrated his administrative acumen. He implemented significant reforms and modernized the British currency system, which had a lasting impact on the country's economy. His work in this role shows that his talents extended far beyond theoretical science. Legacy beyond science. Newton's influence on philosophy underscores how his scientific ideas have shaped the broader intellectual landscape. His theological writings, while controversial, provide a fascinating glimpse into the spiritual life of one of the world's greatest scientists. And his work at the Royal Mint illustrates his ability to apply his keen intellect to practical issues of governance and administration. In summary, Isaac Newton's legacy extends far beyond his scientific achievements. His influence has permeated many areas of human endeavour, shaping our understanding of the world and our place in it. His life and work continue to inspire and enlighten, underscoring the enduring relevance of his brilliant mind.